autonomous or self-driving applications are becoming real in a number of businesses. And construction equipment is certainly one of them, where we want to make autonomous vehicles. When we build any products that are supposed to be on the market, we have to consider functional safety requirements. That is, that products must, they can fail, but they must fail in a way such as that they're not hazardous for people. And these requirements are by law and some other. I'll get to that. And very early we have to consider what architecture is suitable to actually enable us to certify this product. It certainly is a very complex product, and we have to build it in such a way that we can certify it for functional safety. That's my talk today. I'm presenting work that we have done together with Volvo Construction Equipment in a project where we are building a producible self-driving hauler. This is a hauler. And I'm Joakim Froberg, and I'm a researcher for Swedish ICT. But in this project, I'm working for Mälardalen University, so thereby a bit of mix-up of my affiliation. Okay. So the project is called SARPA, and we're actually working on to do the architecture analysis for the system architecture of an autonomous hauler. We investigate what it should do and try to find out what is a suitable architecture. So the safety issue is really one issue in this project, but if we look at the whole hauler, then it's basically, it has relations to, you all know the Google car, and the technology is about seeing what's around you and modeling that and to make the right decisions about how to drive and how to do the tasks that a hauler is supposed to do in its environment. And the important factors here is that it should be able to produce as it's supposed to do in a quarry type environment. And in this project we're evaluating what kind of concerns are the most important ones. But in this talk I'm talking about how to make it certifiable for functional safety. That's the quality attribute type of thing that we're looking for. So what do we want to know? When we're building something like this, early on, there are legitimate questions about how to build a system. Maybe you also have heard a lot of times that people talk about redundancy and functional safety. In this project, we're following a standard that classifies functions into ASILs. It's an autonomous for automotive industry safety integrity level. There are similar standards. So I will talk about the wordings from this standard today, but they're very similar from other standards. So first of all, it's a good concept it's a good idea to get hold of your hazards early in the project. And other reasonable questions that you want to ask early is, we can address safety issues with redundancy and kind of partitioning the system in different ways to make it more or less easy to certify. And some of these decisions you have to take early. So I guess the goal with this work that we have done is to try and come up with some answers early that will enable us to build this system and not to redo expensive stuff later. Okay, so in this presentation, I'm talking about three things. We've done three things. We've mapped out the autonomous hauler application. we use case model the whole thing to see what's actually happening in a hauler's workday, or it's a person's workday today, but it will be the hauler's workday, hopefully. We've done a preliminary hazard analysis for this work, for this precise application, mapped out which hazards exist and which ones are most critical. And we attempt to do system architecture synthesis of this. We try to come up with basic ideas about how the architecture will enable us to certify it later on. Okay. This is what we've done. I'm repeating myself. Autonomous scope and usage of the hauler. And we've made a logic function block architecture from that. Just the logic functions that has to be there. If it's supposed to be enabled to tip and dig and drive around the site like Volvo intends it to, then we have that transformed into a logic function block with a number of functions, and by analyzing those, we can find out which ones are hazardous. We've used the hazard analysis methodology from the ISO 26262 standard. That's an automotive standard that's kind of new in Europe. I'm not sure how it works here, but it's something similar. I know in Europe, it's if you have a product and you want to put a CE mark on it, then and it's a machine type thing, then you have to follow the machine directive, and that stipulates or dictates for you that you have to follow some of the functional safety standards. This is one of them. So there are others, and they're similar. Okay. There we go. This is you've all heard the news. This is getting big. There are many possible applications of this, and it's not one size architecture fits all, because it's really you have to analyze your own system use to be able to make the wisest decisions on your own architecture. Like, for instance, a normal car on the left, that is a picture from the Volvo Drive Me project. It's more on the sense that somebody's supposed to sit in the car and you have driver assistance functions that take over for you. And in the middle, there's a construction equipment application. This one is actually from Australia. This is a Rio Tinto system that's actually working. They have a huge site there with many tens of haulers running autonomously there. And the last one is, it's a prototype from Amazon to deliver packages with a quadricopter thing. I don't know, this is a year ago. Maybe they've done it now, or maybe they didn't do it. I'm not sure. Okay, but the point is that you have to find out your own application to map it out and understand it properly, especially if you want to safety certify it. The safety certification is a large portion of the work, and it's wise to do you want to do as little as possible. One important feature with autonomy is the scope change when we look at functional safety. Today, we have to certify our products today. A normal car, you have to certify that it doesn't fail in such a way that somebody gets hurt. For instance, the steering wheel. It's not okay that it just, this road is somewhat turning, and if it suddenly was going to steer in another direction, it would probably be hazardous. So certifying this system is about really assuring that this function, this blue function that translates the steering wheel's movement to the wheel, is working. But when we consider autonomous vehicles, there is a scope change. Also, this in the red is computer-generated computer functionality that also has to be assured for functional safety. This is a human today, but when we consider this an autonomous system, then the seeing of the road and the perception of all the objects should also be functionally safe. That means probably that we have to see pedestrians and other things. And translate that into decisions of how to control the steering wheel. And that is in addition to the blue type of system that we have today. Okay, so we looked a little bit about the automated hauler application. I'm a computer nerd. I like new things. I'm not a nerd, sorry. I'm just a computer scientist. But yeah, whatever. But this is really fun. It was fun to have a go and look at these machines working. We've looked at a typical quarry type application. These machines, they're general purpose machines. They can run in building sites and stuff. But material handling and quarries are very important. There are many of them. So this is our scope. And what's important, the most important quality attribute is like uptime. It's supposed to be production all the time. And what's happening is that they're loading and tipping and crushing, tipping into crushers and making different granularity of rocks and putting them in piles, and that's the production. Then they get customers and they on trucks to load this material on trucks. What should happen, what will happen is that nobody's in the vehicle, nobody's in the machine when it's operating, but there has to be somebody like a site operator at the control desk. So that's a new type of thing for the usage of this system. The control desk most likely will be at the site, but in the future that could be in a city somewhere that's not so remote. Many of these sites are remotely located, and a future vision could be that people work in cities instead. There is also, we have to consider that it's a mixed fleet of vehicles here. For sure, Volvo doesn't want to have a mixed fleet. They want all the machines in the world to be Volvos. But it's not going to happen, or I don't think so. And so there's going to be a mix of all types of brands of machines, and they have to interact safely. And there's a little bit of resistance between these machine companies to follow standards. They want to do what's best for them, of course. But it's also mixed in the sense that it's mixed. There's both human operators and automated vehicles or machines in these sites. So it can be kind of a. If all the machines were non-operated by humans, then there would be less hazards, because hazards are defined as when you put a person under danger. So it's not necessarily hazardous if two machines collide. But it's not practical to believe that is possible anytime soon. And it's also impossible to assume that these sites could be completely shut off from people and vehicles. It doesn't seem to be possible from what we have found out. Okay, now we get to, so that was so far we have mapped out the application about an autonomous hauler, what it's supposed to do and not do. Now we get to the preliminary hazard analysis. A little problem here is that the Volvo and the other companies are sensitive about these types of hazard analysis, so I'm presenting an example. You've heard the story before? Yeah. It's very similar to a real thing. Just to explain what it is and how it's done, a PHA in F, if you follow the ISO 26262. If everything else works fine, you find each functional box and you assign severity to it. You assess it with these three parameters. There's severity, exposure, and controllability. So for instance, if you have a function, you have to see pedestrians, so detecting pedestrians, perceiving that there's a pedestrian around the car. The hazard is you could have a fatal collision if you just don't see people around you. So the severity, there's different grades of that. That's a possible fatal. S3, the toughest one, and exposure is, there's not people all the time around it, so it's not the highest exposure factor. But it's very low controllability, it's a C3. It's basically difficult to jump away if this 50-ton machine moves towards you. And that you combine that according to some table in the standard, and you end up with a severity, integrity level, safety integrity level of C, the second highest one. There's ASIL A to ASIL D, where D is the highest one. Okay, so we do this for all the function blocks, and we end up with classified hazards for all the functions. We have about 100 hazards classified when we've done this. We can, if we don't detect pedestrians or vehicles, we can collide, and if we fail to tip our load properly in pockets, we could injure people. Okay. I should say something more. This whole standard is when you design a system, there's a lot of work to do to follow the standard, and it's all based on process requirements. You have to do a certain type of documentation and certain hours of testing, lots of stuff, and it all depends on this ASIL level. If you have a lot of ASIL Ds, you will have to do a lot more process around this product. And it's considerable. You want to, if possible, you want to have a useful product without so many high integrity levels. That should be preferable, because you know it's going to cost you. And thereby you want to reduce that cost. And the standard provides ways to do decomposition. And it means to use redundancy. If you have an ASIL D function, you could do it as a single channel function, but you will have to test it a lot, and you will have to document a lot of things. You will have to prove that it's beyond doubt works. Or you could, if you have an ASIL C function, it's fairly difficult and costly to certify it. You can reduce it to 2 parallel systems, which you're then allowed to treat them as an ASIL B and an ASIL A, which is considerably lower requirements on. So it could be, for instance, an ASIL C. If you have an ASIL C, you have to have external assessors coming to your organization to check if it's fine. If you have a redundant system with an ASIL B and an ASIL A, which the standard allows, you could maybe have an easier, more enabling your own organization to work efficiently. So these types of considerations are important. And it's important here that in safety consideration, this is the only reason that you do redundancy. So you do redundancy as a way to enable you to certify your system. It's not safer, not in the eyes of the standard. You have to be safe, but you can be as safe if you do it redundantly, if you spend less effort on each of the channels. Yeah, I think it's at least this standard, some other standards are not so clear, but this standard is very clear, I think, about, it has a whole section on how it allows you to separate this acyl decomposition, how you do that. So, okay, now we get to the last point, the last point. Now we did the application and we did functional or preliminary hazard analysis. Now we get to architecture from an autonomous system. This is from a reference framework of how to do autonomous decision-making software. For starters, if we look at this system, it's just we need to have a world model about what's happening around us. To do that, we have perception functions to see what's happening around us. And based on that, we calculate the behavior. How should we drive? Where should we turn the wheel? Where should we lift the bucket? Based, of course, on what mission goal we have. If we want to tip our load on a pile. And then we have the real world, and the action is probably, hopefully, the action turns out that the pile turns out the way we wanted to, and by sensing it, we sense that we get the right 3D shape of it, that was our mission goal. Okay, this is just a way to separate the software functions. And now comes the trickier part. These models, all of them are used in different levels of a decision stack. The same type of model that we saw here is implemented in each layer of a decision stack. And the idea is that on a high level, we have high-level abstraction about how many vehicles are moving. And at the low level, we have the control functions for how to move the actuators. And there's everything in between. The standard doesn't say exactly what these levels should be. You can do that yourself, depending on your own application. But it's on a high level, it's a long time frame, perhaps several minutes ahead. And at the bottom, it's it's the control functions. And to the left, we have we talk about sensor fusion. All the sensors get merged in with clever algorithms to detect people and to detect whatever is around us. There's also a map involved. You can get data from a map that says where you have your piles and where you have houses and forests and roads, whatever. Similar to an autonomous car in traffic. Okay. So when it runs, there could be input coming from the map saying that this is where the road is. We have also sensor input saying where other cars are or other machines, and there is sensor fusion processing going on, and it ends up with actuator control to steer us in the right direction. And to tip the bucket if that's necessary. So an example, detecting vehicle. We need to detect it. There's a function to plan a trajectory where we should drive, and there's an execution of that. I can't show you the exact functions, so I just classify them into detection, planning, execution, and actuator functions. And because I want to show how this makes some implications for how to build this architecture. Detection functions are in the sensor fusion part of things. It seems reasonable, and it's fine. Then we have planning functions and we have execution functions. let's skip out the analysis. We plan a trajectory where we're going, and we have an execution of that trajectory. It's for us, for certification purposes, we should, it seems to be a possibility to just keep a limit on the stack and keep these functions as low as possible, because if we do, then all the hardware and the software functionality below that level will require us to do all this extra process to assure safety. And we can probably do the stuff that's above that, we can probably use a more normal development process, which seems to be a good idea. We also saw in this study that a lot of the lowest level, the actuator control is really hazardous. It's involved in all the movement of the machine, and it seems that there could be really a super high safety integrity type of system at the bottom to allow us to have actuator control. Let's keep that on that one. One conclusion from this is that redundancy seems to be very applicable when you look at the perception side of things. If you remember what we saw here, the detection functions, there you can make redundant all the sensors and stuff. But it seems really difficult at the behavior level. It's when you have a decision-making algorithm, it's not necessarily a good thing to make it redundant. It seems just complex. And there is a possibility to restrict classified functions to the lower levels, layers, and that seems wise. So it's not a super strong conclusion. It seems very reasonable to do a PHA early, and it can aid in your architectural decisions. It doesn't tell you everything, but it's fully possible to do it very early, and it seems wise to do it that early. You get some guidance. If you do that, you get some guidance on how to separate critical subsystems and how to do the redundancy, how to apply redundancy to enable you to certify the system easier. It certainly seems best suited for the perception functions. That's about it for me. Thank you.
We have a few minutes.
It seems that working in a quarry or a construction site is kind of an extreme environment. So what I didn't see, and I'll ask, is the health of the sensors.
Yeah.
Do you factor that into the system that provides the safety? In other words, most systems, all systems that have sensors have a built-in test functionality for that sensor.
Yeah.
Is each sensor functioning properly at any given time? And obviously, if I don't have properly functioning sensors, then the quality of my decisions is going to drop. So can you talk about what are the hazards to, mud, dust, rocks from a human-operated machine breaking a sensor, and how you work that into your calculation?
It really seems to be a hard problem in this context, because it's very, very dusty. And even if you instrument all your sensors with that you detect when it's covered, when it's too dusty and dark and rain and muddy, then you would have a system that ends up standing still a lot of the time. It's safe. Safe but not very useful. And it's a whole other dimension. I'm not an expert on this, but those people tell me that it's going to be a problem. And I didn't talk about that detail yet. We're not quite there yet, but it's certainly a concern that will have to be addressed. Conditions are bad sometimes.
I think like that's where redundancy and perception comes in, right? You can have different ways of proceeding. Maybe it's the holding mechanism that decides where everybody else is right.
Yeah.
But another question is, Seems like behavior might also be influenced by failures, right? Like if you're in the middle of dumping something and a hose breaks.
Yeah.
A hydraulic hose breaks. You know, what?
Yeah. We
I mean,
didn't.
I'm sorry. I'm not
Yeah.
about these safety standards, but is that even?
Yeah, it is. It is possible. For now, this was the first preliminary hazard analysis. But as we go along and implement things, then those types of scenarios will also have to be included. That could certainly be one. That's difficult. I'm not sure how to.
Put it off there just for a second to say we're at the time limit, so if you have to leave to the break, you're free to go. Maybe we could hang around here for a few more minutes. I want to remind everybody to there's a voting card for today's presentation, and there's an overall evaluation form for the whole conference. Remember to grab one of those and fill it out. I'm sure there's a registration desk too.
Great.
If you could hang around for a few minutes.
Yeah, I'm hanging around.
Yeah.
I'm fine.
About the equivalence between ACL-C and ACL-A plus ACL-B.
Yeah.
Is it like a generic rule? How can you know that they're equivalent?
Yeah, it's you can't. You just the standards just dictates how this is how they see it. They've made a judgment call that.
Yeah, and do they like specify constraints or rules that you have to comply with to use that equivalent? Can you just always decompose an ACL-C and ACL-A and ACL-B?
Yeah, always. And but that was just one. They have a section of and a number of like 15 different ways that you can decompose in, and that was one of them. So if you have an ACL-C, you can decompose it into an ACL-B and an ACL-A, or there was some other way.
2662 is focused on electronic and software kinds of things.
Yeah.
It doesn't cover every possible.
No, that's true. I didn't say
That's
that.
just the way the ISO group.
I should have said that. Yeah.
It's used here, but it's
Yeah.
not a regulation.
Okay, it's not a regulation.
Not yet.
Not yet. Yeah.
So everybody's trying to comply and be good players so that the government doesn't step in and
Yeah.
force regulation.
Yeah, okay.
Everybody's doing
That
the right
seems-
thing on their own.
It seems
They
good
don't need
enough.
the regulation, and that's easier to do.
Like for the Google cars, for example, or autonomous cars, or Tesla, so like a set of regulations that they have to comply with, or is that state dependent?
I
federal?
think it's, just the
not
ability to
sure.
put them on the roads is state by state. And only a few places have said you're allowed to put a car like that on the road.
Yeah, like
So it's a very emerging area. It's very interesting.
Yeah.
I wasn't even thinking of this kind of application, of big haulage
Yeah.
trucks, because I work for Ford, so
Yeah.
it's all passenger car stuff.
Yeah. But that's
So how much, so you flashed through a little bit, but I see something there where you distinguish the architecture between what's on board the machine and what's remote. How much of it is most of the brains on the actual truck, or is it all
those
central controller?
those are good questions. In a way, you want as much as possible logics outside the vehicle, because you could have a center where you could coordinate all the movements and stuff. But maybe you run the risk of not being able to contact each and every one at any given point. And you certainly have to do enough power of calculation to see people and to keep your safety critical functions up. So it's a trade-off. We're not there yet for this application to know. But the stack, it can be over fleets of functions. So that could be at the center somewhere.
I guess your stack keeps going up until it covers really the whole site.
Yeah.
There's something that just decides and then goes right down to the actuators at the
Yeah.
highest level.
Yeah, there's people in the project who's looking into how to optimize movements with energy consumption, because it's a big thing here that you shouldn't spend too much energy by doing. Drivers apparently we're not good at that. They hit the pedal as hard as they can, and then they run to where they stand waiting for 5 minutes. So, and this could be improved.
I could imagine like with taxis. There's
Yeah.
some taxi drivers
Yeah.
that drive like
Yeah.
maniacs, and some that very slow.
That's
Just cars on the highway, like braking, accelerating.
Yeah.
It can.
Thanks for hanging around. Thanks for the
Thank you.
presentation.
Thank you, guys.
Enjoyed it.